So our first topic will be rectangular geometry. All right, so let's take a look at our first topic, which is going to be our schedule. So today, July 25th, again, we're going to be over time complexity. Space complexity is not as relevant, but yeah, so we're going to be going over time complexity and rectangular geometry. We'll move on to simulation, complete search and brute forcing tomorrow, which is also a really important topic that you guys need to know. And then we'll go over some more data structure based and algorithmic stuff on Wednesday. Graph theory, really essential to competitive programming, depth first search and breadth first search, some important graph algorithms. And then Thursday and Friday, we'll be going over prefix sums and binary search.
Okay, but before we go into the new topics, let's review. So, I want you guys to take a look at this problem for like the next maybe like 2 minutes just to get started. You can let me know if you need more time, but just like look at it and just try to gather up some thoughts and anything that might come to mind, and just type it if you have any idea. Hello, Goku. We're just basically going over a problem right now. So yeah, there's people who are just like solving it, and just want like, if you have any thoughts about this, you can put in your input as well. So Rushel said in chat, we can use pairs to help with this problem. Definitely, yeah. You can see like there's the 0, 0, the coordinate style of like inputs. So pairs definitely could be used here if that's one way you want to approach it. So yeah. If you have any other thoughts about this problem, just leave it in the chat. Okay, so it's been like 2 minutes since I've shown this problem. If anyone needs any more time, please just let me know, and I can wait a little longer. But yeah, if no one needs any more time, then I'll just get started with the explanation. So as Rushel said, you definitely can use pairs to store it. So yeah, I mean, I guess I could work with that. So I want to store. Okay, before I go into the actual problem solving, let me just read it out so everyone knows what's going on. So there is a pasture. Okay, he wants to create a triangular pasture, and then there's n fence posts at distinct coordinate points on a 2D map of his farm. Okay, so there's specific dots that are on. Okay, someone else entered. Okay, so basically for this problem, there's n distinct dots that can be placed on the 2D coordinate map of his farm, and he wants to choose the 3 of them such as one of the sides is parallel to the x-axis and one of them is parallel to the y-axis. So he wants to choose a set of 3 posts of the end post such that it forms a right triangle. And what is the maximum area that this right triangle can be? So Continuing on from last week we did a lot of simulation. So like here, this is essentially the same thing. So if we want to find the maximum, a very brute force and simple way to do this is just to test every single possible combination of three posts. And then once we test every single combination, we just compare them to each other. And the combination that gives the largest area is our answer. So we will get into time complexity this this lesson, but I'm not going to do this now. But just to keep in mind, this number sometimes is important, but in this case, 10 to the fourth is not super large in the context of a lot of USACO problems later on, but we'll go into that in depth more later. So I'm thinking that in the range 10, okay. So we have three different points that we can have, and we basically just want to generate all possible points and then find the area, right? Like as I said. So I have the code that I typed over here, and I did file IO because this is an older problem. So you're gonna need to do file IO to practice those. Okay, so I read in the inputs, which is the number of points. And then I did use two separate vectors here, but you could use pairs, as Rushel said. And I basically just read in the inputs into these two different vectors. So then I have a running maximum counter, which is best. And then I have three for loops. So basically what this is going to do here is that like it's going to generate all the different possible points. So it's going to go through and generate like all possible points. And then if you think about it, like here, okay, so it's saying, you might be wondering like what these comparisons are. So if we like picture a right triangle, and then it says over here, like, you can choose 3 points as long as it's a right triangle, basically. That's essentially what he's saying. So basically, since I know it's a right triangle, I can choose 1 point to be the corner, which is I. And then J, another point will need to have the same Y value. So I can set this to J. And another one will need to have the same X value. So in this case, like this is K. And I'm generating all possible, I'm making each one go through every point so that I'll test every single possible combination of the corners and these possible points. I'm basically generating every possible combination. And if I generate a right triangle using this combination, which is this what it's checking, then I will check the area. And it's possible that like K could be here, right? And then in this case, like we might get a negative area outputted from this function if we do like base times height. Oh, and by the way, it says 2 times, so I don't need to do like divided by 2, because like, you know, a triangle area formula is base times height over 2, but it's saying output 2 times. So I'm just going to multiply base times height, which is essentially what this is doing here. But also I need to add an extra check because sometimes the area might be less than 1. I mean, it might be negative if I have like a negative, quote unquote, negative height here. So I have a check for that. And then once I calculate the area, I'll compare it to the running maximum here. If it's greater than it, then I'll just replace it. Otherwise, it will just remain the same. And after going through every single possible combination of points and checking the maximums, I will output my answer. So that's it for that question. Okay. So now we've gone over a lot of useful simulation problems, but I mentioned before that you'll need to know how efficient your code is and if it'll meet the USACO run times, like if it'll run in time, right? So let me go more in depth on what that specifically means. How can you know if your program will run in time for you to code it up? So time complexity is the measure of the number of operations an algorithm performs. So I'll go more in depth about that later. And USACO problems, the number of operations are around 5 times 10 to the 8th, or around 10 to the 8th operations. So that means given the input, the coder must find an algorithm that will allow it to execute on the input size under this time complexity. So what this means is, let's say I have an n to be of size 10,000. So that's 10 to the 4th. If I used a linear algorithm, which is like O of n, then that would just be n itself. So that would run in 10 to the fourth time, which is less than 5 times 10 to the eighth operation. So you always want to be making sure, like, before you implement, you want to make sure, like, does it fit under this time complexity restriction? Then you can try to implement it because you know it could potentially be a valid solution. And here on the top, I basically just highlighted 3 essential terms, but in terms of use code, the one on the left is the most useful, and I'll explain why. But the other 2 are just useful to know just for like theory in general, like on the higher level, you might need to know this theory. So let me start from omega. So omega is basically just your program is guaranteed. In the best case, it'll always run this fast, like the fastest it could ever run. Um, so like, let's say you were trying to do a for loop, and then you check the first element, and then like if it's equal to 1, then break. So then the best case is if you had an array and the first element's the element you're looking for, you just break instantly. Then that's you just did it in one operation. But worst case, you could iterate through the whole thing and not find the element you want. And worst case, you do linear time complexity because you'd be searching through the whole array. But then here, the best case is O1 because I just broke immediately. So omega is basically all about like, okay, what's the fastest my program can run at? And then theta is the average case. So whenever my best case and the worst case are the same, then I have an average case, which is theta. Sometimes theta doesn't exist, but whenever your best case and worst case are the same, then theta exists. And I'll go over some example problems later. So you can see when theta exists or when it doesn't. And then big O is the big one you're going to be looking at when you're talking about use code, because use code is all about you want your problems to run fast. So why would you want to check the best case? You want to check the worst case every time, because if your program meets the worst case, then that means that no matter what input use code throws at you, it'll always run in time, because at the worst case, it meets the 5 times 10 to the 8th limit. So yeah, so let's say like your program like runs under like 5 times 10 to the 8th, they'll always work. So you always should do the math here. Like as I said here, like if you're using an O of n algorithm with a 10 to the 4th input, then overall the operations will be 10 to the 4th, which meets this. So like from now on, I'd encourage you to think about what algorithm you're using, and which I'll help you establish with some examples. And then you should be able to know the time complexity and then apply it to your input size to determine whether it might run into. So here are some common examples of runtimes and algorithms. So accessing an array element. So if I did like array of 2 or something like that on an array, that's constant time. So that's why this is a very useful feature of arrays. You can do it really quickly. So like, even if I had an array of size like 1 million, if I did array of 2, if I try to access that element and see out array 2, that's only constant time. So that's something very important to keep in note. Here's the binary search algorithm, which I have not gone over yet. If you want a rough definition, we'll go over this later on Friday, but if you want a rough definition of what binary search is, it's kind of like if you're reading to a dictionary, you split it in half, and then and then if your letter is lower, you go to the right. If your letter is higher, you search to the left, right? So you keep on like going different, splitting your dictionary in half to look at whatever direction you want to go towards. And this is much more efficient than just like searching every page one by one, like to find the word you want. So binary search basically is essentially just splitting it in half in the direction you want until you find the specific element you want. And that's the rough definition, but I'll go over the specific implementation later. And this algorithm is really useful because as you can see here, it's super efficient. And on the right, you can see how efficient this is. Like seriously, like log n is like, you barely can even see it like over like O of 1. So like, as your input size n goes to like 10 to like the 16th or something, if they throw something insane, like log n will handle it easily. Like that would be an extremely efficient implementation. Like it would be around like 16 operations, like give or take. Like instead of like, if you did a linear time complexity on 10 to the 16th, it would be like 10 to the 16th. So yeah, binary search is something that's like really useful. And I will teach you guys that skill later. Iterating through array, as I just said before, is just like going through every element. So imagine like use code said, okay, your input size is 10 to the 16. And then if I made an array of that size and iterate through it, I'm not going to pass any case. Well, I might pass like the default case, but like I'm not going to complete that problem because that's just like way too inefficient. You can't do 10 to the 16th operations because as I said before, the maximum is 5 times 10 to the 8. So as I said before, you should definitely do the math in your head based on like your input size, like might I meet this problem's requirements? And that will allow you to see if you're using a good algorithm. Okay, sort algorithm. This is relatively fast. It's not like n times log n. So whenever you just have an array and use the sort function as I said before to sort it, like as I described, you can do it like this. If you have an array plus n, which is like, we're gonna assume this is the size. So that would sort the whole array. This is n log n. Or if I want to sort a vector, let's say I have a vector named vec. So vec dot begin, and then vec dot end. So both these commands I'm calling are going to take n log n time complexity. So just keep that in mind. And then also, yeah, it does show what n log n's look like. So you can see that it's definitely considerably higher than these. So if you have extremely large input, it might not be able to do that super efficiently. So just keep that in mind. And then nested loops. So if I just have nested for loops, like I have a for loop on the outside and then for loop on the inside, as we went over last week, and then I iterate through it, that would be n squared. So there's that. And then recursive Fibonacci. So you might be wondering why I'm saying this is 2 to the n. I can show you this. So like, let's say I call Fibonacci. Let me just draw out what a Fibonacci might look like. So here, if n is less or equal to 1, then I'm just going to return n. It should, if you do a Fibonacci, it should look something like this, and then return fib n minus 1 plus fib n minus 2. So basically, so let's say I called Fibonacci on like 5 or something. So I'll go here, and then now I'm going to call 4 and 3. And now I'm going to call 3 and 2. And now I'm going to call 2 and 1 on this one. And this is going to return 1. And this is going to keep on going down. And this is going to return 1, 0. And this is going to return 0. This is going to return 1. This is going to, like, as you can see here, it just like each function call basically splits into 2 separate ones. And then if you count the layers, okay, let me just show why this represents Fibonacci. So basically, Fibonacci is just like 0, 1, 1, 2, like basically every single element adds up to the previous one. So if I want to find like the 5th element of Fibonacci, I want to add up recursively all the bottom nodes. I want to see, I want to get the sum of every node below that. So that's essentially what I'm doing here. And I can explain that clear later, but I just want to show why this 2 to the n time complexity. So the first layer, you can see it's 2 to the 0, 2 to the 0 elements. So it's just one node. Second one's 2 to the first, 2 to the second. And if I did a larger input, you would see a consistent trend, which is like, it'll keep on going, like 2 to the third or whatever. And then, but then eventually, like if I called Fibonacci on like n, just like an arbitrary n, the last row would be 2 to the n. And then in terms of like a geometric sequence, like since the rows keep on going by 2 every time, whenever you have a geometric sequence of operations like times 2 times 2 times 2, the bottom row always dominates the time complexity. So in terms of recursive Fibonacci, if I keep on doing these calls, I'll eventually get a 2 to the n time complexity because the bottom row will have 2 to the n nodes. So I can say the overall time complexity is 2 to the n because I said whenever you're doing a geometric sequence in terms of amount of function calls, the bottom row will dominate the time complexity of the operations. So as you can see here, you definitely do not want to be doing recursion on Fibonacci. You want to be doing a more efficient algorithm. Like if I did Fibonacci on like 30 or something, I don't even know if my code would be able, my IDE would be able to handle that. It probably would, but like actually I don't even know if it would, but like whenever like even like for really small numbers, like it can scale really badly. So like whenever you're doing Fibonacci or any other algorithm, I wouldn't recommend using 2 then. It's just not really a fast algorithm. So try to avoid it when you can. And then now we just have n factorial. Like you're never going to use this in competitive programming, but like you could, but like on very small emphasizes. So overall, you want to be trying to get the fastest you can in competitive programming. That's how it works. So yeah. So let's go over some asymptotic analysis, which is just determining the worst case, best case runtimes uh, of our problems based on what it looks like. So I'll give you guys like 30 seconds for the problem on the right here. Anyone wants to say their answer? So what do you guys think the runtime of this is? Just like iterating through a loop. If an element is equal to what I'm looking for, I mean, if an element is true, then I'll break out. So does anyone want to say like what they think best case time complexity is for this one? Like best case? If I get a true Boolean, I'll break out. Like what do you guys think the worst case is? I mean the best case. Okay, yeah, the best case. Okay, so if nobody has any thoughts about this, I can go over my logic for it. So I have an array of size n, right? Let's say just n is like 3 or something, just to keep it simple. But like in terms of asymptotic analysis, as it says here, you should always assume n is trending towards infinity. But let me just draw it out because it's like, easier here to show. If my first element is true, then it's just going to go in here and it's just going to return 0 instantly and I'm going to break. So if the first element, so it's going to check, like basically what this algorithm does is it iterates through the whole structure. And then if any element's true, it's going to return 0. But like since the first element is true, it's just going to break instantly. So best case, my time complexity is O of 1. Or theta of 1, technically. That's my best case. I'll just write it. Actually, I'm gonna write it like this. So my best case would be omega 1. That's like the fastest it could run, right? But worst case is I iterate through the whole array and I don't find any truths. So basically, the worst case is I just iterate through the whole thing, and that's my worst case, which is O of n. So in terms of competitive programming, you always want to be focusing on the O of n case. So hold up. You always want to be focusing on the O of n, like the worst case runtime, because that's going to be most useful to you because USACO's going to throw a lot of like harder inputs. They're not just going to give you an easy input where it can run fast. But let me screen share because now you go to the next page. Okay, so in terms of USACO, as I said, you always want to be focusing on the worst case runtime. So it says there that it's O of n for the worst case, and then best case, it can run at constant runtime. And here, I'm just gonna go over Fibonacci, as I said before. So like, you might think like, okay, wait, so what if the user inputs 1? Like, wouldn't it just break out and then instantly, and then it'd just be like constant time, right? Like this something like I might have thought before too, before I really studied this stuff, but like, it doesn't, you're not allowed to do that because n trends towards infinity whenever you're dealing with the runtime. Like you always have to think of it in terms of that. So basically, since n is like trending towards infinity, you can't think of it as just like 1 and then breaks out instantly. So because of this, the worst case and the best case runtime is the same for Fibonacci. And because I said whenever they're the same, there's a theta value that exists. So the average case is theta to the n for a recursive Fibonacci function. Okay, now I'll go over this problem on the left. So what's the worst case runtime? I'm going to focus on worst case runtime from now on because you always want to find out where your code's the slowest because that's what's going to be most essential to you in terms of like solving these problems. Okay, so it's not as I said before, the best case is not just constant, and you should know why. It's because n trends towards infinity, so it's never going to break out in terms of our evaluation. But we're not looking for best case here; we're looking for worst case. So let's compare. We want to find the worst case, right? So the worst case is not the first one because like you don't want it to break out instantly. You want to run as many times as possible. Now, if we compare n minus 2 and n over 2, I believe the worst case would be this running this call every time because if I kept on running n over 2, my n would decrease much faster than if I just subtracted 2 every time. So therefore, like since there would be more overall operations when I only subtract versus dividing by 2, then I'll have an overall slower time complexity if I use test n over n minus 2 every time. And like it says if n is even essentially over here, if there's no remainder when I divide by 2, right? So if n is even, then I'll keep on calling test n minus 2. So if we just keep on subtracting 2, a number could be even every time. So we could think like it'll never go into these calls until it's less or equal to 0. Then it'll go into this call. So essentially what I'm doing is I'm calling n here, and then I'm just calling like n minus 2. And then by 1, I mean it's constant. So each function call, every time just call a function that's constant. But I'm doing these function calls this many times. And I'm going all the way down to 0, which I'll break out. So it looks like since n minus 2, n minus 4, I'm decreasing by 2 every time. I have n over 2 elements. So theoretically, you could say like, oh, okay, so doesn't that mean I'm running O of n minus 2 times 1, because each element is 1. So this is my runtime, right? Well, we never consider these constants when we're calculating runtime. So we can say that the worst case, our program will run in O of n. And then let's go over the problem on the right. This one's a little bit trickier, but like, let's just go over it. So like, so on the outside, we have a loop, and then we have a nested loop on the inside. So like maybe some of you are thinking, oh, is this n squared? Because like it's a nested for loop, right? Well, nested for loops are only n squared if you iterate it by like if you iterate like just by like plus plus or like plus equals 2 or something like that. Like then, but like here, as you notice here, there's a times equals 2. So that complicates our situation a little bit. So let's like just draw it out and see what this might be doing. So j is becoming 1, then 2, and 4. Okay, so let me keep track of I first, just so I don't get you guys confused. So I is currently 0. So j, it's 1, then it's 2, then it's 4, then it's 8, 16. And then eventually it'll become n over 2 and n. So the time complexity is the number of operations, right? So how many times am I multiplying by 2? Let's think about this. So the first row, if we see this pattern, it's actually 2 to the 0. This is 2 to the 1. This is 2 squared. This is 2/3. And this is interesting. So like, since we noticed this, 2 to the power of x equals n. Okay, so this is the 0th element. This is the first element. This is the second element. So basically, the amount of the last one is the x elements. And that means there's like around x total operations going on. I'm multiplying x times. So if I found out this number, then I'll know how many times I'm multiplying. Now, like, let's see. Like if I did log 2 to the n, then I can essentially cancel these out due to our log properties, and I'll get n. So basically, if you think about it, our worst case for this problem, for this inner loop, is log 2 of n. But in terms of time complexity, we can drop the basis. So our inner loop is running at log n. And then our outer loop will continue to iterate outside of that, just like 0, 1, 2, 3. And then the inner loop will keep on doing this same thing. So instead of doing n times n equals n squared, like we would do for like just an iterative nested for loop, we'll do n times log n because that's what the inner loop is running at. So now we know that the time complexity of this is n log n for the worst case. And then here's another one. So I'm basically just creating a vector of size n, and then I'm doing an iteration through it. So let me see. So it's a plus plus b plus plus. So that means like we can see that it should be running n squared for these loops, but let's confirm our suspicions. Okay, I'm assigning a random element. No, I'm making the first element in the array a random number from 0 through 99. That's what this does. And then I'm sorting it. And then as we mentioned before, a sorting function is n log n. And then the outside loop is running n squared. So the worst case of this is simply just n cubed log n. Okay. Now let's go to, this is my last asymptotic analysis problem we're gonna be doing today. So let's get the size, and then we're getting a sum. So now we're doing 0 through n, we're iterating from 0 through n, okay. So we're thinking like 0 through n, and then we're gonna have j equals I, and then it's less than n. Okay, so I equals 0. Let's see what happens. So when I is 0, j is 0, and then we're gonna do j. We're gonna iterate j until it's 1 less than n. Then we'll break out. So we're doing 0, 1, 2, 3, all the way to n minus 1 in the inner loop. So in the first loop, we're doing n operations. But now I'll iterate through, it'll become 1. So now we're going to start from 1 instead of 0. So we're doing 1 all the way through n minus 1. So now on the second loop, we have n minus 1 operations. And then if you see this pattern, the amount of operations will decrease all the way to, eventually it'll become just 1 operation. Okay, so that's how the pattern of this goes. So how can I figure out the time complexity? Well, since the operations are consistently decreasing like this, we might be able to recognize a formula. So 1 plus 2 plus 3 all the way through n. If you guys haven't learned this yet, I believe like a lot of teachers teach it somewhere in high school, like 9th grade or something. But you might have heard of it a little earlier, or maybe like even like 7th or 8th grade if you're into like competitive math, maybe even earlier. But if you want to sum all the elements from 1 through n, the formula is n times n minus 1 over 2. So now that we have this formula,
it should be +1.
oh, n times n plus 1
Yeah.
over 2. Okay, yeah. So we have n times n plus 1 over 2. And then this is proportional to n squared because we can see the n squared plus n over 2. And then the n squared term dominates here. It's the largest term. So this is the only one that will matter in the final time complexity. Because when it grows, those small n terms will not be growing as fast as n squared. So we only want to care about that. So our worst case time complexity is O of n squared for this expression right here. Okay, so that's it for the asymptotic analysis. And if you guys had a little bit of trouble with that, feel free to leave questions. And don't worry, a lot of USACO problems are a lot more straightforward than the example I just showed you. Like a lot of them are just like, okay, a nested for loop, n squared. Okay, so like, okay, sorting function, okay, n log n. Like a lot of them are more straightforward. So just get some practice and you'll be able to evaluate the time complexity in terms of big O of your expressions in the future or your algorithms. So let's go on to rectangular geometry now.
Okay, so before we go into rectangular geometry, Brandon, could you pull up like Desmos? I want to show everyone something about the time complexity.
I mean, I already showed the graph. Okay.
Yeah, just like basically, you guys might be confused a little about like why we're dropping terms. So here's what Brandon said earlier. So he was saying something about how n squared can be compared to n times n plus 1 over 2, right? So if we have n times n plus 1 over 2, we can distribute it like Brandon did. So this will be n squared plus n over 2. And what he's saying is we can just call the time complexity n squared. We don't need the plus n over 2. So here's the reason why. So if we're typing the function x squared plus x over 2, like basically x is just n, right? So as x approaches infinity, as the number of operations becomes infinitely large, you can see that the two functions are getting closer and closer to each other. So the x and x over 2 don't really matter as x approaches infinity. So as the amount of operations increases more and more, the two functions are more or less the same. So that's why we're not caring about the x over 2. So this is just to illustrate why in time complexity, we're considering dropping the constants, dropping the numbers. So as another example, Brandon, you could type in like x squared and you can type in like 3x squared, for example. So again, similarly, there's a reason why we don't consider constants inside the time complexity or big O of n. We can just call this x squared, big O of x squared, for example. And the reason for that is, as you can see in this graph as well, as x approaches infinity, or like the amount of inputs approaches infinity, it really doesn't matter whether we have that 3 or not. You can still see that the overall time complexity or worst case scenario for how many operations the program will have to run is basically the same thing. So that's why we don't have any numbers inside time complexity. We mainly have variables.
So you can see like, look, like x squared is extremely inefficient. Like with a small input, it goes up really fast. X is right here in the middle. It's much better than n squared, but look how like efficient log n is. Like you always want to be chasing like the efficient algorithm. Like look how like it's basically just a flat line, right? So whenever you're running an algorithm like this, you're going to be like, you should be pretty confident that you're even in the higher levels like silver and gold, like you will be able to pass your cases if you implement an algorithm like this correctly. Because literally just like a straight line, like it can pass basically any input size, like almost any like that use code throughout you. So that's basically, yeah, just something you need to keep in mind, time complexity.
Yeah, so that's like basically a visualization of basically what's happening, how fast the computer is being able to execute operations on the y-axis. Well, the y-axis is basically going to represent the time it's spending, the number of operations based on the input of like how many, what's the input basically. So
Yeah.
next we'll be going over our essential topic for today, which is rectangular geometry, our first competitive programming intro topic. So what is rectangular geometry? This is going to mainly deal with sets, intersections, and unions of rectangles. So if you guys learn sets in math, that can be useful here. You can apply. So just some quick tips over here. We suggest drawing out and simulating scenarios for this topic and creating different cases of possibilities. So over here on the right, we can see kind of like a picture of some rectangles over here. So we usually competitive programming, they're going to give you something like the bottom corner in the top corner. So you can see A, X1, Y1, and top right of this big rectangle is B at coordinates X2, Y2. So think about this as like a coordinate plane like you see in math. Like if you guys had taken algebra 1, for example, like so basically on a coordinate plane, it can give you the coordinates of the corners of the rectangle, and you're going to be able to find out certain intersections between them, stuff like that. So that's why I was mentioning sets and unions of rectangles. So here you have another smaller rectangle, C x3, y3, and D x4, y4. And essentially, we're just having that green area over there representing the intersection. So this kind of idea of what we're going to be doing in this topic. So let's go over our first problem here. So this is the USACO 2015 December contest bronze problem 1. It's called fence painting. So basically, I'll read the problem and I'll go over the solution. So I linked it here in case you guys want to see it after today's lecture. So I'll read the problem here. So several seasons of hot summers and cold winters have had taken their toll on the fence, and he decided Farmer John is going to basically repaint it with his favorite cow, and she doesn't understand Farmer John's instructions. Usually USACO will just give you some kind of story or like outline of like where the situation came from. You don't really have to worry too much about it. So here's like where the real problem is going to start. So if we regard the fence as a one-dimensional number line, Farmer John paints the interval between x equals a and x equals b. For example, if a equals 3 and b equals 5, then he painted an interval length of 2. Just 5 minus 3, right? B minus a. So Bessie, misunderstanding Farmer John's instructions, paints the interval from C to D instead of A to B. And this section that she painted may overlap with part or all of Farmer John's intervals. So it asks us to determine the total length of fence that is now covered with paint, right? So as input, it'll give us A and B. A is less than B, and it'll also give us C and D. It tells us C is less than D. This is guaranteed for sure. It also tells us A, B, C, and D all lie in the range 0 to 100. So there's two main approaches we can take to this problem. The first one is the more inefficient way, and that's why I'm not going to be using that as the main solution, but this is something to keep in mind. So since you see over here that A, B, C, and D are all within 0 to 100, we can kind of just draw a 2D number line as the problem states. It's a, sorry, not 2D, 1D. Just draw a 1D number line. So the range of the integers A, B, C, and D are all between 0 and 100. So we know that A, B, C, and D are all around here. So let's just say A is here, A is less than B. So let's just say B is here, just as an example. So like I said in the last slide, you can draw out cases of different possibilities of the arrangements of A, B, C, and D. And then based on these cases, you can determine your solution. So let's just use this as like a general simple case, just a starting case. I know there's more cases, but we'll go over that in just a second. So essentially, if we have every value between 0 and 100, well, a computer can easily just solve all 100 operations, just perform all of them really quickly. A human can't, but a computer can. So like Brandon said, it was 5 times 10 to the 8th operations that USACO can handle. So essentially over here, 100 as like the number for the limits between A, B, C, and D is like nothing. So you don't have to worry too much about time complexity in this problem, but just something to consider. So if we have A, B, C, and D, we're given the values as input, we can kind of just loop through this entire 1D number line and just calculate the area over there. And if we find an intersection, then we could just subtract the area and not count it, right? That's one way to go about it, but that's kind of more inefficient because we're going through the entire 0 to 100. In this case, it doesn't matter, but because it's the limit of A, B, C, and D is 100. But let's say instead of 100 as the limit, let's say it was like 10 to the power of 10. Then you wouldn't be able to pass the USACO time limit by using this method because you're going through every single point in time, every single part of the fence, right? So between 0 and 100 is like the length of the fence, I guess you can think about it that way. And if the length of the fence was 10 to the power of 10, you wouldn't be able to go through this entire fence over here and just simulate the situation and then print out the intersection or like not count it in, right? There's too many operations for your computer to handle. But in this case, of course, like I said, there's only hundreds here, so you're able to do that. So I'll be going over the faster solution. So Brandon, could you go to the next slide? All right, so here's basically our solution here. So I'll be going over the key idea and then some cases and then the code. So let's start off with the key idea. The key idea is basically to sum the space covered so far, and then we're going to subtract the total intersection that's involved. So basically, we're going to basically create cases now. So let's say that basically this problem is giving us A, B, C, and D, and it's telling us to get the total distance covered, right? So there's several cases. Let's draw out the first one. So let's say on this massive number line over here, let's say 0 through 100, right? This is the range of A, B, C, and D. Let's say A is over here and B is over here on the number line. And let's say C is over here and D is over here. So in this case, the answer would be D minus A, because that's the total length of the distance covered, not including the intersection, right? So this entire length will be our answer, D minus A, because we don't care about the intersection between C and B, right? That's the part that we don't want to include. So the whole answer will be D minus A. So what we can keep in mind originally as an algorithm to solve this problem is we can get the lengths individually. We can get this length and get this length. And using these two values, we can add them together and then just subtract the intersection. And that'll give us the leftover length. So just to demonstrate it more clearly. So let's say instead of having this number line to be messy, let's say this is A and this is B. Then this entire interval's length is B minus A, right? Let me delete that. This entire interval's length is B minus A. And similarly, we can have something like this for the interval C and D. And the total length of this interval will be D minus C, right? So what we can say is the total area covered or distance covered from these intervals is going to be D minus C in parentheses. I can add B minus A to get the total length covered over here and over here. And now all I have to do is subtract the intersection. So let's look at the intersection here. It's just basically this box, right? So basically I'm going to subtract the intersection. So basically the ambiguous part of this problem that we haven't mentioned yet is basically how you're going to find the intersection. Well, that depends on the placement of A, B, C, and D. So in this case, I want you guys to observe that, let me clear this quick. A, B, oops. A, B, C, and D. Here's the intersection over here. I'll just draw the box out and shade it in. So this is our first case that we want to make, right? First case is that the CD interval has partial intersection with the AB interval. So let's create case 2. So I'll just draw it out here. There's not too much space. Case 2 is going to be, let's say A and B is this interval. And C and D is going to be behind that. So C is going to be here and D is going to be here. So in that case, the intersection section will be over here. Let me shade that in. That's the intersection for that case. So that's we've generated 2 possibilities. Cases are just possibilities. Just think about it that way. The third possibility, again, there's not much space. I'll draw it out here. Is let's say that the interval A and B is like over here and over here. And C and D, let's say the interval covers from here to here. This is where Bessie painted the part of the fence. So in that case, the intersection is over here. And finally, the last case, case 4, that I'll just draw out, is basically going to have C and D on the outside and A and B on the inside, in which case the intersection is this section similar to case 3. So let me shade that in quick. So here's the observation that I want you guys to make. The intersection of the, an intersection has a start and an end, right? There's a start of the intersection section and an end of the intersection section. So what we need to do is find those two. We need to find the start of the intersection and the end of the intersection and just subtract those two. We want to subtract this intersection length, and then we've gotten our answer at that point. So here's how we're going to find our intersection start and find the intersection end. I want you guys to notice after drawing out every case, make the observation that the intersection end is right here, for example, right? It's always going to be the minimum between B and D. And over here, in case 2, that's case 1. In case 2, we're looking at the minimum between D and B. That's going to be the intersection end. Over here in case 3, the minimum between D and B is going to give us the intersection end. And similarly for the last one, sorry for the handwriting again, the minimum between B and D is going to give you the intersection end. So the formula that we derive from looking at these cases is the end of the intersection is going to be the minimum value between B and D. So min of B and D. And if we want to get this intersection start, we're going to apply a similar observation. Look at case 1. The maximum value between C and A is the beginning of the intersection. Similarly, in case 2, the maximum value between A and C is the beginning of the intersection. And likewise, in case 3 and 4, the maximum between A and C is going to be the beginning of the intersection. So basically, that's just going to be the beginning of the intersection. And we've been able to get the start and the end of the intersection. So all we have to do is subtract these 2 values. And we've been able to get the total intersection area that there is. And if we want to get the amount of paint that's covered, that's not involving intersection, you just have to sum D minus C plus B minus A. So in any case, there's an interval A, B, C, D, for example. So I'm going to add this B minus A. I'm going to add this entire interval length. I'm going to add the entire D minus C length. So I'm going to say temp is equal to D minus C plus B minus A. It's going to give us the total distance covered. And I want to subtract the intersection, right? So all I have to do is set a variable. We're going to say integer intersection equals maximum, I'll clear this quick, equals maximum and minimum B and D. So like I said, when I was drawing out the cases, I'll draw one out again. So I'm going to take the maximum okay, here, I'll simplify this. So we'll start over here. The minimum value between B and D is the end of the intersection, right? So the minimum between B and D is going to be B in this case. We're going to take the intersection end, and we're going to subtract the maximum value of A and C. So we're going to subtract A over here, subtract C over here, sorry, because that's the intersection start. It's the maximum between A and C, and that'll give us the intersection start and end. We'll subtract those two, and that'll give us the total intersection covered. And if they're not intersecting at all, like A, B, and C, D, then the intersection will be negative. So we'll just say the intersection value is between this value and 0, either one of those two. And then we'll just say the answer minus equals intersection and print it out. So that's the idea behind this problem. Just for a time complexity analysis, that problem runs in O of 1 time because we weren't looping through anything. We weren't going through between 0 and 100. We weren't going through this entire number line and basically like simulating the situation. We were just taking the maximum, comparing some values and printing them out. So that's why it runs in O of 1 time. So let's take a look at the second problem. So I won't read the whole thing, but I'll basically give you guys the gist of it. So essentially, it's going to give you a billboard A. Just think about billboards as a rectangle. And I'll give you billboard B, right? And it's also going to tell you that A and B don't intersect at all. So that's nice to know. And lastly, it'll tell you that there's basically, let me find it. There's a truck over here. It's going to either block one, both, or none of the billboards. So the truck could be over here. As one, the truck is basically another rectangle. Just think about it that way. A truck could go over one of the billboards, or the truck could cover both of the billboards over here or something like this, right? It could overlap with both of them. So it's basically telling us to output the total area of both billboards that remain visible. All right, Brian, could you go to the next slide? Yeah, so here is basically the key idea of this problem. So I want you guys to notice that billboards all have a certain property in this problem. So if I have a billboard like this, I can have the bottom corner as x1, y1, like as in a coordinate plane if you were to plot this on a coordinate plane, and the upper right corner is going to be x2, comma y2, right? So every billboard has properties. So since that is given, I can give a hint about how we can use a class to represent this. So here I made a class, or you can also make a struct, but I just made a class. I made all that stuff public because in a class, the default values are private, like we mentioned last Friday. And every class is going to have a bottom corner, bottom left corner, and an upper right corner. So that's why I have these fields here. And the area is just going to be, like I said, this is x1, y1, and this is x2, y2. You just have to get the difference in the x coordinates, which is, and the difference in the y coordinates, and just multiply them by each other. That's going to give us the area. So that's basically going to be the structure of creating a billboard in this. So here in our main function, I'll start off here and move on. So in our main function, we're going to read in the input, and we're going to create a billboard for the billboard A, billboard B, and the truck. So that's basically what this problem is giving us. So we're going to read in the values. Is a bit messy, but yeah, we're just going to read it in using cin. And essentially what this problem is asking for is asking for the total area covered that's not obscured by the truck. So again, as an example, A, B, let's say the truck here. Let's assume the worst case as there's an intersection between the truck and both billboards. So I'm going to add the area of A. I'm going to add the area B. So that's going to give us here, and that's going to give us here, right? But we want the area not covered by the truck. We have to subtract. Let me change my color quick. I have to subtract this intersection, and I have to subtract this intersection. That'll give us the total area that's not covered by the truck, right? So basically, I have to subtract the intersection between A in the truck and B in the truck, and that'll give me my answer. So if I want to calculate the intersection, I made a custom function for that, so you guys can kind of see how the code is organized. So over here, we're going to take in the two billboards and take two billboards, like arbitrarily, any billboards. We're going to put them in as parameters because every billboard is different, right? So I'm going to just set dx and dy here as two variables. And then I'm going to say the maximum. Okay, let me label this actually. So let's draw out the cases for this. So let's say I have a billboard here, and this is x1, y1, and this is x2, y2. And this is billboard 1. But I want to find the intersection with another billboard. Let's say this is billboard 2. And I have another bottom right corner. I have x1 again, y1, and x2, y2. So basically what I'm doing here is I'm going to say I want to find the intersection area, right? That's what this is. I want to find the intersection area so I can subtract it over here. So I'm going to take the minimum value between x2 I'm going to take the minimum right corner of the x values. So in this case, I'm going to see that this is x2, this is the first x2, and this is second x2. I want to obviously use this one, right? I want to use this one, so that's why I'm taking the minimum. And I'm going to take the maximum of x1 and the other x1. So I'm comparing the x1 values. There's one here and one here. We want to take this one over here, as this is the one that includes the intersection. So I'm going to take the maximum of that, and I'm going to subtract these two. So I'm going to get the difference in x over here of the rectangle, and I'm going to do the exact same thing with y. And basically, we're going to get the area by multiplying the difference in x and difference in y of the intersections. I'm going to return this value. So that'll give us the total area of the intersection, which I'm just subtracting. And once we do all this math out, we basically got our answer. And again, this problem is going to run all one time because we're basically going to be just performing normal operations and comparisons. We're not using any for loops or recursion or anything like that that Brandon showed earlier. So it's going to run in constant time, which is really efficient for this problem.
I noticed that's 11. So if anyone's really busy, you can just leave, and we'll release the homework and the homework and the slides and recording later. But if you want to stay, we can go over this last problem.
All right, so let's read this problem. Again, as Brandon said, if you guys have anything to do, you guys can definitely go right now. But for anybody who wants to listen to the last USACO problem, then here it is. So Farmer John has decided to update his farm and simplify its geometry. So previously he's had 2 rectangular pastures and he wants to replace them with one of minimum size that covers the entire area. So let me just draw this out quick. So I know that we're like a little behind on time. So let's say we have 2 pastures like this. He wants to make a pasture that covers the entire area that this does with minimal like excess area, right? We want to cover all regions enclosed, but have it minimum size. So obviously, if we want to have it minimum size, we don't want to have like a big gap over here, right? Because then we're going to have extra space over here, and we don't want that. That's not the optimal solution that the problem's asking for. So essentially, what we're going to do is we're going to have the pasture like this. We want to have the pasture cover everything that the yellow part does, but we also need to make it minimum length and minimum width. So it's going to give us the 2 coordinates over here. So it's going to give us 6, 6, 8, 8, 1, 8, 4, 9. So basically, these are the corners of the rectangle. So x1, y1, and this is also x1, y1, but for the second rectangle. And this is x2, y2 for the first rectangle, and this is x2, y2 for the second rectangle, right? So basically, what we're going to do, essentially the idea, is if we want to find, let me change my color again. If we want to find the fence that covers this entire section of without like excess area, we're going to get the maximum y value and the minimum y value, the maximum x value, and the minimum x value, right? And we're just going to multiply those two together. And just to mention quick, so it says that so this problem is called square pasture, which means the shape of this pasture needs to be a square, which means a square has the same side lengths for the length and the width, right? So the area of a square is s squared, right? That's why it's called a square. So here, if I want to have a square pasture, that means that I need this length to be same as this length. I need x to be equal to y, right? But it's not necessarily the case if we're going to be given these inputs. So what we need to do is say, okay, is x greater, like basically we need x and y to be the same value. But if I make x too small, it won't cover the entire area we want to. If I make y too small, again, it won't cover all the area we want to. So we need to take the maximum between x and y. So we want to make sure at least that the entire area is covered. And then we're just going to square that value because we're going to take the entire length. Even if we have x area, it's okay because we need the square. We need the pasture to be a square instead of a rectangle as given the problem. So that's optimal. So again, what I was mentioning in this diagram over here, again, like if you're doing rectangular geometry, we highly recommend you draw out the cases on pencil and paper. Don't just like envision it in your mind. We want you guys to kind of draw it out and visualize it as much as possible so you guys are as clear on the algorithm as possible. So again, what we did in this algorithm is we took the maximum x coordinate and maximum y coordinate that they gave us. So I know this is really messy, so I'll just break it down. So if I want to find the maximum value between like x1, x2, x3, and x4, then I can't write it like this because this function max only takes in 2 inputs, A and B. It doesn't take in 4 inputs, it only takes in 2. But let's say I want to compare 4 values. I can do it like this. I can say it's the maximum between A and another object. I can say, not A, sorry, x1. And the maximum between A and another object is going to give me the maximum value, right? So instead of having one object here, I can do a little trick. I can say maximum of x2 and x3, because this is only one number, right? I'm only comparing 2 numbers total. I'm just using max over here. So basically what this is going to boil down to is maximum of all this is going to give me the maximum value of all the x coordinates. I'm going to subtract it with the minimum of all the x coordinates. So that's basically going to give me the total difference in x. So if I have like again, the billboards over here, and I have the big rectangle covering all of those, I want to get the total x distance. I want to get the total y distance over here, right? So I'm going to subtract the maximum and minimum x coordinates. Sorry, I shouldn't draw x. I reversed x and y. So this will be x and this will be y. So I'm basically getting the total length of x over here by subtracting the maximum x coordinate and the minimum x coordinate. And similarly, I'm going to do the same thing. I'm going to subtract the maximum y coordinate with the minimum y coordinate. And then I'm going to basically just square the value of the maximum between x and y to get the total area of the square. So as you can see in the key idea, find the maximum difference between the x and y coordinates, create a square around this max value, and just calculate its area by doing the length squared. And again, this is going to run O of 1 time because all we're doing here is doing comparisons. You can say like each of these is an operation, right? O of 1 means one operation, or like basically it means one operation. But basically, like you can see, like no matter how many operations we have, like 20 operations over here, let's just say like we just simplified to O of 1 because it's, like I said, just like how we dropped earlier when we showed the visualization of Desmos, we dropped the values of constants like because they're not significant as n approaches infinity. Over here, it doesn't really matter either. It's just constant. There will always be the same amount of operations done by the computer, regardless of what the input is. So it's going to run an O of 1 time, which is constant. And finally, we'll go over today's homework. Basically, there's going to be 3 problems over here, all related to kind of rectangular geometry, if you guys want to challenge yourselves and try it out. But yeah, we'll be going over this tomorrow. But yeah, thank you everyone for coming. I know this lecture went on a little longer than we were hoping to, but thank you for everyone who sticked around. And we'll go over tomorrow's homework tomorrow. And yeah, basically, that's it for today. Thank you everyone
Also,
for
like
coming.
another thing, just try to like when you're doing these problems, try to think of like time complexity, like how fast am I running, just like another note. But yeah.